Hi, Naveen. Good evening. Sorry, I got held up a little with some work, so uh, I'll just start in 2 minutes. I'll just share my screen. Hi, once again. So, can you please tell, or you can write in the chat box as well, if my screen is visible and is my voice audible? You can write in the chat box if you cannot unmute yourself. Hello. Hi, Naveen. So, can you please write in the chat box if you cannot unmute yourself? Is my screen visible to you and am I audible? Yeah, hi. So Akshit, am I audible to you and is my screen visible? You can write in the chat box if you can't unmute.
Good evening, sir. Yes, your screen is visible
Yeah,
and you are
yeah.
audible.
Thanks, Akshit. I'll just start. Sorry, you got held up with some work today, so you could log in only at around 6 or so. So um, we'll anyway make up for that. Okay, so I'll just start now. Let me put it in full screen and right. Okay, so we'll just start. So questions from 1 to 10 are actually given in the portal itself. In the portal itself, there is a tab called Assignment 5 Solutions. So question numbers from 1 to 10 are given in the portal itself. We will of course see how to solve those questions, but we will keep that for the last. So for now, I will start from question number 11. Okay. So let me go to question number 11 and then we will start from over there. And then we will come back to question numbers 1 to 10. Okay. So we'll just start off. So diode bridge rectifier capacitor filter uses a resistor to limit the starting inrush current. What should be the minimum value of the resistor in ohms? Consider the supply voltage as 230 volts with a 20% tolerance. Diodes have a maximum surge current rating of 50 amperes. Okay, so how do we solve this? You know that we have our AC voltage source, and then you have a switch over here. Correct. And what they are telling us, they are using a rectifier, a resistor to limit the starting inrush current. Correct. So typically, what you have is something like this. And you know that if initially the capacitor is uncharged, right? If the capacitor is uncharged, then you know what's going to happen is if C is uncharged, then when during the positive line cycle, that is when you have this is your VAC, correct? So during positive line cycle, you of course know that this diode D1 and this diode D2 are going to conduct, correct? So the current flow path would be something like through this, through the output, and through diode, correct? So this would be the current flow path. So since you can see in the circuit that there is no impedance at all, or you can say the impedance is very minimal, what you would actually observe is that the current would be really large, correct? If C is uncharged, the current high starting current would be very high, right? And this is what we actually call as the inrush current. Okay, so one of the basic methodologies of actually limiting this inrush current, right? That is, how do we actually limit this inrush current? Correct. So one of the basic or very basic methodologies is actually to add some resistor. Correct. So you know that resistor actually limits the current value. Correct. So what did we do? We added a current limiting resistor. Okay. So we added a current limiting resistor. Okay. So they are asking us what should be the value of this resistance? What should be the value of this resistance? And given that the supply is 230 volt, if it is given that as 230 volt, you of course know that it refers to the RMS value. If just the number is given, you know that it is the RMS value, not the peak value. So it is 230 volt with 20% tolerance. And they have also given that maximum surge current rating of the diode, right? Maximum surge current rating of the diode is 50 amperes. So if you go to the device data sheet, they generally give two current ratings, okay, in the device data sheet. So let me actually take a new slide over here. Yeah, so in the device data sheet, they generally give two ratings. In the device data sheet, one will be what is known as the continuous current rating. Okay. And another one will be surge current rating. Okay. Surge current rating, or it is also known as pulse current rating. Pulse current. Generally, the surge current rating or the pulse current rating, as we call it, it can be into 2 or into 3 times the continuous current rating. Okay. So it can be into 2 or into thrice the continuous current rating, which means that, okay, under steady state, the diode can take only this much amount of current normally. But let's say during transients or maybe once in a while, right, it can take higher current, that too for a very short period. Okay, it cannot, of course, take in that much current for a prolonged period, right? So it can take in a very large current, or I should say twice or thrice the continuous current rating for a very short period of time. So that is what is known as surge current rating. You know that if the capacitor is uncharged, right, then obviously there would be a huge current, and that current would be used in charging up the capacitor. So as the capacitor voltage increases, the current will obviously go on dropping. Correct? As the capacitor voltage increases, the current goes on dropping. So you know that this huge current is actually going to come only during the starting period, not during the normal steady state operation. Correct? So we can assume the maximum surge current rating for calculating the resistor value. Okay, because that is going to happen only once when your capacitor is uncharged. Once the capacitor is charged, of course, the current rating would go lesser. Correct? Now the question is, how much resistor should I add so that the current is limited to 50 amperes? Okay. So you of course know that your V in, if it is something like this, so this is your V in, your rectified V naught is going to be something like this. Correct? Assuming it's a full bridge rectifier, your rectified V naught will be something like this. But since you have the capacitor, what you're actually going to see is, if your capacitor is uncharged, it will rise till the peak value. And then after that, once the V in actually starts dropping, your capacitor obviously cannot discharge that much fast. There is no dissipating element. Therefore, your capacitor will slowly discharge. Correct? It will slowly discharge to some value. And then again, it will rise up till the peak and it will slowly discharge. It will slowly discharge. Then again, it will rise up. Then it will slowly discharge and so on. Correct? So this will be your capacitor voltage or your actual output voltage. Okay, so you know that this particular point, so this point is your V max or V peak. Okay, so this will be your V max, and you will be having a ripple with respect to the minimum point. So this ripple, let me call this as delta V. Okay, so this defines the V min point, and you know that V max minus V min equal to the capacitor voltage ripple or delta V. Okay. So now the question is, but moreover, you know that just to charge up this capacitor, for the voltage to actually rise, correct? For the voltage to rise from 0 towards the peak value, obviously the capacitor will draw current. Okay. So the current would look something like, there would be huge current during this period. Then the current would go to 0. And then from this point only, from this point onwards, the current will be obviously lesser. Okay. So your capacitor current is going to be something like this, correct? During the starting, your capacitor is uncharged. Therefore, the current would be very high. Then further on in the further cycles, so this is your I. So in the further cycles, since the capacitor is already charged, what would happen is you only need some current to raise the capacitor voltage from Vmin to Vmax, Vmin to Vmax, from Vmin to Vmax. So since the delta V is lesser, the current is also lesser. However, in the starting, the delta V is very high, correct? The capacitor voltage is 0, but your Vin is obviously increasing. So you will see a huge current. Now the question is, I want to limit this particular value of current. Okay, I want to limit this current to some I peak. What should be the resistor value that I choose so that the limit current is limited to I peak? That is the question. Okay, what should be the resistor value so that the current is limited to I peak? Okay, so how do we solve that? We will obviously choose resistor for the worst case condition. Therefore, your V max, correct? What is your V max? 230 volt. It's your RMS with a 20. Your V in is actually V in RMS is actually 230 volt plus or minus 20%. 20% of 230. Okay, so this is your V in RMS. So if you have calculators, please do calculate. Okay, so you have something like where's my calculator? So 0.2 into 230. Correct. So what is this? Plus 230. So you have 276 volts as your maximum RMS. Correct. This is the worst case RMS. Therefore, your VM will be 276 root 2. Since the input is an AC sinusoid, your VM will be 276 root 2 volts. Okay. So what will be your R? R minimum will be equal to Vm divided by I, correct? I surge current rating. So I surge current rating has been given as 50 amperes in the question, 50 amperes. Therefore, your R required is 276 root 2 by 50. Okay, so 276 into root 2 divided equal to 7.806. Okay, so this is the R that is required. Okay, right. Yeah, so 7.8 ohms. We have got 7.806, correct. So you need to have an R value which is greater than this number so that your current is limited to even lesser values. Okay, right. Okay. So let me see if there are any comments on the chat box. Capacitor is causing interest. Yes, of course, because the capacitor is uncharged and there is no other load in the circuit. Okay, load or any dissipative element or current limiting element in the circuit, correct? Because during starting, you know that the path is going to be directly through D1 through the capacitor. The capacitor is right now uncharged, correct? So an uncharged capacitor is essentially equivalent to kind of a short circuit. As the capacitor builds up, the current will obviously go on decreasing, capacitor voltage builds up, but still, right, that would be a huge current and it would complete its path through D2. So essentially it's like it provides a direct current path for VAC with no resistive element in between. Okay, so that is what causes the interest, and we want to limit it. That's why we are having a current limiting resistor. Okay. Okay. So we'll go on to the next one. So this is regarding the MOSFET based inrush current limiting circuit that you might have studied in the lecture slides. The figure shows an inrush current limiting solution for the diode bridge rectifier capacitor filter circuit. Voltage of 12 volts to remain in the ohmic region that is desirable to reduce the power loss of the MOSFET. Okay. At steady state, the ripple in the output voltage is 73 volts, neglecting the MOSFET drop. What should be the ratio of R1 by R2 for flawless operation of the circuit? Supply specification is 230 volt, 50 hertz. Okay. So question may seem difficult, but it's quite simple. I'll just take a new slide for us to solve. Anyway, so what have they told? So what they have mentioned is that, okay, so yeah. So what they have mentioned is the MOSFET requires a gate source voltage of 12 volts to remain in the ohmic region. Of course, you know that MOSFET can operate in three regions, correct? One is the cutoff region, that is MOSFET is totally off. And one is what is known as the saturation region, right? Here the MOSFET is on, and one is known as the ohmic region, and again MOSFET is on, correct? And this is evident if you actually draw the VA characteristic of the MOSFET. Okay, so if you go through the VA characteristics, so this is your VDS and this is your ID. Okay, if you go through the VA characteristic, you will see something like and so on, right? So this is for increasing value of VGS. So VGS equal to, let's say, 2 volts. This will be VGS equal to 15 volts. So you have a number of curves in between. Okay. So we know that so you know that this particular region wherein the MOSFET doesn't conduct at all. So this is your cutoff, correct? And this is your ohmic region, correct? So regions over here are the ohmic regions, and the slope over here will be equal to delta ID by delta VDS, which is equal to 1 by RDS. That is the channel resistance. Okay, 1 by channel resistance. Okay, so the drop across the MOSFET in the ohmic region, voltage drop across the MOSFET will obviously be ID into RDS, correct? And in the rest of the region, that is in these regions, you have the saturation. Okay, wherein VDS is fixed irrespective of the current. For a particular VGS. So in saturation region, you know that the MOSFET behaves like a voltage controlled current source, VCCS, voltage controlled current source, and the channel current or ID will be given by GM times VGS minus VTS the whole square, correct? So you can understand from this equation itself that if your VGS is set, your I channel is also set. Okay, so obviously it behaves as a current source, voltage controlled current source, and the drop will be a fixed drop called VDS. Okay, and that drop is actually going to be very high. So obviously what you will do is you want your drop to be as small as possible, correct? So you will operate in the ohmic region. Okay, you always want to operate in the ohmic region because you want your drop to be as small as possible. So your voltage drop ID RDS is very small. Why? Because your RDS on will be of the order of a few milliohms. So if your RDS is on is in the milliohms, with respect of your current, even if your current is a little bit high, since your RDS on is very small, the overall drop will be very small. Okay. So anyway, so this was some extra piece of information, but the idea is in power applications, you always want to operate the MOSFET either in the ohmic region or in the cutoff region. Okay. In saturation region, we generally do not operate MOSFETs for power applications. But if you go towards signal applications like maybe in your analog circuits, you always see MOSFETs operate. Want the MOSFETs to operate as a current source in that case. Okay. Here we want the MOSFET to operate as a switch. Okay. So in the cutoff region, you are operating the MOSFET like a switch. In saturation, MOSFET operates as a voltage controlled current source, and again in ohmic region, it is a switch. It's an on switch and it's an off switch. Means this is open and this is a short. Okay. So anyway, so what they have given is the MOSFET requires a gate source voltage of 12 volts to remain in the ohmic region. So what you want is across the gate source. So in this picture, so this is your gate and this is your source. So across the gate source, correct? Across the gate source, you have 12 volts. Okay. So 12 volts, you have 12 volts over here. If you assume this is the ground, you have 12 volts. So that is, you know that from this particular statement, you have your VR2, that is VR2 or VGS of the MOSFET, both are same. Obviously, from this picture, VR2 is actually 12 volts. Okay, so this is one information. And they have also given at steady state, ripple in the output voltage is 73 volts. Correct? So ripple means we just saw that. So this is your ripple, right? That is the delta V. Correct? That is, you have this, correct? So you have something like this, correct? Let me draw it properly. Not yeah. So what they want to mention is your ripple is 73 volts, which means that your ripple would be something like this. Let's say it's your capacitor voltage. So then your ripple would be this is your delta V. This is your V max and this is your V min. Okay. So what is your V max? V max is obviously equal to your peak input voltage. Okay. So Vmax is peak input voltage, and they have also given that ripple in the output voltage is 73 volts. So which means that your delta V is 73 volts. Delta V is 73 volts. Okay. And Vmax, what is Vmax? Vmax is peak input voltage. Your supply specification is 230 volt RMS, correct? So let me take another slide. Yeah. So we were just writing that VR2 is 12 volts. Delta V is 73 volts. What is your Vmax? Vmax is 230 volt RMS. So 230 root 2 is your Vmax. Correct? So which will turn out to be somewhere around V25 volts if I'm right. Correct? So 230 into square root 2. Yeah. So it will be 325.27 volts. And they have given that delta V is 73. Therefore, what is Vmin? Vmin will be Vmax minus delta V. Vmax minus delta V, which is 325 minus 73. Turns out to be 252.27 volts. Okay, so this will be your Vmin. So they are asking what should be the ratio of R1 by R2 for flawless operation of the circuit. Okay, so what is R1 by R2? R1 by R2. So you know what is VR2, correct? And they have also given that MOSFET is in the ohmic region. So if MOSFET is in ohmic region, correct? Correct. If MOSFET is in the ohmic region, voltage drop across the MOSFET, or VM if I write, it will be I MOSFET into RDS on. Okay. So that is what we just saw over here. That will be the voltage drop across the MOSFET. Okay. But for now, they have told that you neglect the MOSFET voltage drop. So we need not worry too much about that. So they're asking us to find out what is R1 by R2. Since it's a proper resistor, you know that R1 by R2 is equal to VR1 by VR2, correct? The voltage across R1 divided by voltage across R2. So if you find out VR1 by VR2, you get the answer, correct? You know what is VR2? VR2 is 25 volts, 12 volts. So just we need to find out what is VR1. If we find out VR1, we know what is the answer, correct? So is this question clear to you? Just look at the chat box once. Correct. Yeah, so okay. Okay. So we just need to find out what is VR1 by VR2. Yeah. Okay. So we just need to find out what is VR1 over VR2. Right? And we are aware of what is Vmin, Vmax and all from the given properties. Right? So if you go back to the circuit, so this is your VR1. We know what is VR2. So this is your VR1. We just need to find out what is this. Okay. So if you kind of neglect the voltage drop, right? So if you neglect the voltage drop, then what would be VR1? VR1 would be equal to your VC out. Correct? Correct? Your VR1 will be equal to your VC out, or which is your V out. Okay. So the question is, what should be VR1 over VR2 for flawless operation of the circuit? The idea is that you want your MOSFET to be on for the worst case condition. Correct? So what you would want is, even if your output voltage is minimum, correct? Even if your output voltage is minimum, I want my MOSFET to operate. Okay. So only then, even for the minimum condition, if your MOSFET is operating, of course it will operate for the maximum voltage scenario. Okay. So what you would want is, even in your VR1 is equal to V minimum, you want the circuit to operate. Therefore, you know that V minimum is 252 volt. Therefore, VR1 over VR2 will be equal to what? 252.27 that is V min, divided by your VR2. VR2 is 12 volt. So what is this? 250 divided by 12. So divided by sorry, so it's not exactly 250. It should be, just a second. So your VR1 should be equal to total voltage minus VR2, correct? So and there is a small mistake over here. So your VR1 will be equal to total voltage minus VR2, correct? So your VR1 will be equal to your V out minus VR2, that is your VR1 divided by VR2, correct? So your V out will be 252.27 minus 12 divided by VR2 again. So VR2 is 12. So 252 minus 12 is 240. So 240 by 12 is almost 20. So this is your ratio of R1 by R2. Okay. Or this is the condition for which MOSFET will be turned on. Okay. So you should choose your resistors accordingly. Fine. So this is VR1 by VR2. Yeah. So you got your Vmin, which is 252. So the MOSFET should be on during the minimum output voltage. Therefore, your VR2 should be 12 and your total VR1 plus VR2 will be obviously your V out, that is 252. So you know that VR1 will be 252 minus 12, which is 240. Therefore, VR1 over VR2 will be 240 by 12, which is 20. Okay. Okay. So let's see here. So which are the correct statements about inrush current limited to rectifier circuit, related to rectifier circuit? Inrush current is a startup transient phenomenon in rectifier circuits. Yes, it is true. It occurs during startup. A diode's repetitive peak current rating indicates the maximum permissible inrush current through it. No, a diode's non-repetitive peak current rating. Correct? Because the diode can withstand that particular peak current only once, it cannot withstand multiple times. So a diode's non-repetitive peak current rating indicates the maximum permissible inrush current. Okay, a diode cannot go on withstanding the same surge current every time. Okay, or during every switching. Okay, it is supposed to occur only once. Resistance connected in series with the supply can protect the circuit from inrush current related circuits. Of course, yes, resistance is like a current limiter. A thermistor with a positive temperature coefficient will be an efficient solution for inrush current protection. No. A thermistor with a negative temperature coefficient. Okay, and all of those, of course, no. Okay. Thermistor with negative temperature coefficient will do, and diode's non-repetitive peak current rating indicates the maximum permissible inrush current that you can push. Okay, and that is supposed to happen only once, of course. Okay. Okay, so we'll go on to the next question. A rectifier circuit is protected from inrush current using a series resistance of 200 ohms, operates at a steady state. So what they have given is again a resistor based question. Your RS is 200 ohms. The rectifier is connected from 230 volt supply, draws 0.5 amperes sinusoidal current at unity power factor. Okay. So your V in RMS, of course, is 230 volt. Okay. draws 0.5 ampere sinusoidal current. Okay, and so your I in RMS is 0.5 amperes at unity power factor. Okay, it has an output voltage ripple of 20 volts, that is delta V is 20 volts. Okay, so from the given data itself, you can understand that your V max at the output will be 230 root 2, which is 325.27 volts, and delta V is given as 20 volts. Therefore, your V min is V max minus delta V, which is 305.27 volts. Okay. It has an output voltage ripple of 20 volts and connected across a 500 ohm resistive load. So R is 500 ohms. Okay, what is the operating efficiency of the rectifier circuit? So what is the efficiency? Efficiency is typically given by P naught by P in. So in the output you have a resistive load, therefore I can write I square R, or I can also write it as V naught square over R, correct? V naught square over R divided by P in. P in is V in RMS into I in RMS, correct? So this will be my efficiency. Okay, that is P naught over P in, correct? And they have not given any diode drop, and also you can assume that all the diodes are, all the diodes are ideal. Okay, there is no voltage drop across those diodes. Just we need to find out the efficiency. Okay, given your delta V and all. Okay, let me take a new slide. So you know that under steady state, your voltage is going to look something like this, correct? So where this difference is delta V, V max, and this will be V min. Okay, so on an average, you can write your V naught averages V max plus V min over 2, correct? So this will be your average output voltage. So what is that average output voltage? V max plus V min by 2. That is 325.27 plus 305.27 by 2, correct? 325.27 plus 305.27 over 2, which will turn out to be how much? 325.27 plus 305.27 over 2. 315.27. Okay, so this is your output voltage. So now that this is known, efficiency can be simply calculated as V naught square over R divided by V in RMS into I in RMS, correct? So 315.27 315.27 over R is 500 ohms divided by V in I in. So V in is V in is given as 230 volt and I in is 0.5 amperes. 230 into 0.5. Okay. So how much do we end up with? So 230 into 0.5 is 115. and 315.27 square divided by 500. So 98. So I think we are doing some mistake over here. Just a second. So I guess we made a mistake. Okay, so we have not considered the drop. Okay. Okay, so let me redo it once again. Okay, so what we have not considered is the drop, right? That is across the series resistor. Okay, so we need to consider the drop across the series resistor, correct? So our series has been given as 200 ohms. Okay, so we have not considered the drop across the series resistor. So considering that, we need to calculate. So of course, your Vmax will not, Vmax earlier we had written at 230 root 2. Right now it's not just 230 root 2, it will be 230 root 2 minus the drop across the series resistor. Okay, drop across the series resistor. Again, this will be into root 2. Okay, because this is your input. This is your input V in RMS, and then you have your I in RMS, and then you have a series resistor, correct? So the output voltage that gets reflected after the capacitor will be including the drop across the series resistor. Okay, so you need to include that as well in the calculation. Therefore, if you take root 2 common, it will be 230 minus 0.5 into 200 ohms, 0.5 into 200 ohms into root 2. Okay, so this will be your Vmax, correct? So if you calculate that, 230 minus 130, so 130 root 2. Yeah, so it will be somewhere around 183. Okay, so this will be your Vmax. Your Vmin will be Vmax minus delta V, which is equal to 20 volts. So which is equal to, so obviously this is not exactly true. So this needs to be updated, including the RS resistance, correct? Okay. So your Vmin will be 183.85 minus 20, which is 163.85. Okay. So this is Vmin. Therefore, your V naught can be written as Vmax plus Vmin over 2, which is equal to 173.85 ohms. Okay. Therefore, now your efficiency can be written as V naught square over R divided by V in I in. Okay, so 173.85 square over R is 500 ohms divided by V in I in will be 230 into 0.5. Okay. Divided by 500. Yeah. So it turns out to be somewhere around 52.56%. Okay. So obviously you see the efficiency falling because of the current limiting resistor. Okay. So yeah, the current limiting resistor needs to be considered. Okay. There will be a drop due to the current limiting resistor. Correct? Yeah. So now it is fine. We need to include IN into R series drop. Okay. So I forgot to include that in the first calculation, and that's why the efficiency turned out to be really high. Now if we do the calculations, you will get the answer to be somewhere around, efficiency to be somewhere around 56%, 52%. Okay. Okay, so I'll just pause over here and see this. Okay, so RMS theoretical meaning. So you of course know the by definition you know that it's the root mean square, right? That is you do the square of the area and then you take the mean of that and then take a root. But the point is, this is defined as that equivalent current which will cause the resistor to heat up. Okay, that equivalent current which when continuously flowing, okay, when you pass it as a DC, causes the resistor to heat up by the same amount that a DC current would do so. Okay, so for example, you assume that let's say you have a resistor. Okay, so you have a resistor and you pass 2 ampere current through that. Okay, obviously if you pass a current through a resistor, the resistor is going to heat up based on I square R into T. Okay, that will be the energy, correct? So what will be the since this is a DC current, you take the I to be constant 2 amperes. Now let's say that the current through the resistor is not a pure DC. It is having let's say it has a sinusoidal nature. Okay, and the sinusoidal nature is such that it can vary from 0 to let's say some 8 amperes, and then it goes to 0 again, and then it goes to -8 and 0. Let's say for instance it's sinusoidal. It can be any wave shape. Okay, and but point is, but it does not stay properly at 2. Okay, now I am telling that RMS value is that current. Okay, RMS value of any wave shape is that particular current which makes the resistor heat up by the same amount that a DC current would do so. Okay, so if I tell that RMS value of okay, so whatever profile that I gave to you, right? Let's say the RMS value of that profile is somewhere around 5 amperes. If I tell that the RMS of a wave shape is 5 amperes, it means that if I pass constant 5 ampere through the resistor, okay, it would heat up by the same amount. Okay, so it's like you're scaling whatever wave shape you have back into DC. Okay, so that is the point is I square R into T will be same for both cases. So what value of I will make the I square RT same in both a DC case as well as some random wave shape case. Okay, so that is actually the meaning of your root mean square. Okay. So yeah, so don't forget about this I into R series. I just forgot to consider that, and therefore your the efficiency came out to be really high. But point is, you of course know that since in the circuit you have something like sorry, the diagram is not good, but still you have something like okay. So let's say you have a DBR. and then you have the output over here. This is what we were doing. Okay, so obviously the value of V naught will vary based on what voltage you see over here. Correct? What voltage you see over here. The voltage you see over here is actually what? V in minus I in into R series. Okay, so this is a voltage that is actually going to go over here across this terminal. So V naught will be based on what is the input voltage to the DBR, not what is the input voltage from your grid side. Okay, so do not forget this RS. Okay, RS, do not forget this. Correct? Makes sense, right? Because your capacitor output voltage will be based on whatever is the input to the DBR or the diode bridge rectifier. It is not based on whatever is the input to the from the grid side. Okay, so if there is some resistance, do not forget to account for the drop. Okay, and because of the drop, you see that the efficiency is going down and it is around 52% in this case. Okay, so yeah, we'll just move on. The rectifier circuit is protected from interest current using a series thermistor with a cold resistance of 100 ohms and a hot resistance of 40 ohms. So if you tell for a thermistor, you of course know that if they tell it has a cold resistance of 100 ohm and hot resistance of 40 ohms, so cold resistance of 100 ohm is during startup to limit the interest current, and hot resistance of 40 ohm is during steady state. Correct? You would know that from the lecture slides as well. That is when the converter is operating at a steady state, you don't want the thermistor to come into play, because we obviously saw in the previous problem that this particular resistance, series resistance that you have is going to cause losses. Okay. So in order to minimize the losses, people came up with this thermistor solution wherein the thermistor will have a very high resistance, very high resistance at startup to limit inrush current. To limit inrush current, correct? To limit the inrush current and lesser resistance at steady state to reduce losses and increase efficiency. Correct? So this is the idea of the thermistor, that you want it to have high resistance during startup and the same resistance should be lesser during steady state. So that's why you have the resistance notation as well to be something like this. Correct? So it has lesser resistance during steady state and higher resistance during startup. Okay. Okay. So point is, if they have given cold resistance and hot resistance, based on the question, you need to distinguish which is for steady state or which is for transient based on the question. Rectifier is connected from 230 volt AC main supply, drawing 0.4 amperes sinusoidal input current during steady state, and output is connected across 500 ohm resistive load. Okay, so very similar. Peak interest current value during startup is 5 times the input RMS current. So input RMS current is 0.4 amperes. So 5 times that is going to be 2 amperes. Correct? And the output triple voltage is 5% of the startup voltage drop across a thermistor. Output triple voltage delta V is 5% of the drop across the thermistor during startup. What is the output voltage of the rectifier circuit? Okay, so of course you need to account for the drop. Once again, we cannot forget that. Okay, so I will just take a new slide. So we just saw that. So during startup, so this question is regarding startup. So we should be concerned with what is the cold resistance. So I will write the R thermistor to be 100 ohm because you want a high resistance during startup to limit the inrush. So And of course, your V grid, as I will write it, V grid is 230 volt RMS. And it draws input current of 0.4 ampere sinusoidal. Your IN during steady state is 0.4 amps RMS sinusoidally during steady state. Okay. And what have they given? Output is connected across 500 ohm resistive load. So R is 500 ohm and peak inrush current is 5 times the input RMS current. So peak inrush current. So inrush current is 5 times the input RMS current. Peak inrush current, right? So 5 times the input RMS current for 5 into 0.4, which is 2 amperes. Okay. Output voltage ripple is 5% of the startup voltage drop across a thermistor. So delta V is 5% of voltage drop across a thermistor, 5% of IN into R thermistor. Okay, which is 0.05 into what is IN during startup? 2 ampere into R thermistor is 100 ohm. Okay, which will be somewhere around 20 or 10, correct? 10 volts. Okay, so this is the drop across your thermistor. Correct. So delta V is 5% of the drop across thermistor, which is 10 volts. What is the output voltage of the rectifier circuit? Okay, so your delta V is known, and there is of course a resistance. Therefore, the equivalent input voltage is going to be what? V grid minus IN into R thermistor. Okay, so they are asking the output voltage. Can anyone tell me what is the R thermistor should be to be considered? Should it be the cold resistance or hot resistance to calculate the output voltage? Anyone, any ideas? What should be the IN or R thermistor that I should consider? Should it be 100 or should it be 40?
Sir, hot.
Sorry?
Sir, 40.
40, right? Because
Sir,
you know
40.
that, yeah, correct. So you know that this is in steady state. So of course you will consider what is known as the hot resistance of 40 ohm. So this will be hot. Okay, this is okay. So your Vn will be 230 minus In is, of course, we are dealing with RMS right now. So this is RMS. So 230 minus In under steady state is 0.4 into hot resistance is 40 ohms. Okay. So sorry. So 230 minus this turns out to be around 1.6. So 230 minus 1.6 is going to be somewhere around 228.4. Okay, so this will be your steady state Vn. Therefore, your V0 max will be 228.4 root 2. Correct? So 228.4 228.4 into 1.414, that is 320. Oh, sorry, that is 322.96 volt. Correct? and V naught minimum is V naught max minus delta V, that is 312.96 volts, correct? That is V max minus delta V. So your V naught average will be the average of these two, obviously, that is going to be somewhere around 317.96 volt, somewhere around this, correct? So yeah, so your IN is okay, I think there is a calculation mistake here, correct? Because your IN during steady state only we should consider. Therefore, steady state is given as 0.4 amperes, correct? So 0.4 amperes, and our thermistor is 40 ohms. So 0.4 into 40 is just 228.4, correct? And V naught max will be root 2 of that. So V naught min will be minus delta V. Therefore, V naught is something like this. So here I think there is a calculation mistake. So I guess they have not considered the correct value of R IN. Okay. Okay. So which are the correct statements from the following options? A low power factor leads to high line losses as compared to high power factor for the same load ratings. So in rectifiers. Oh. Yeah, so steady state, because in the given question it was given right, sir. So hot resistance is considered. Of course, I guess we have done correct, right? Hot resistance was only considered over here. So 0.4 into 40, correct? Because in the question it is mentioned that hot resistance is 40 ohms and input current is 0.4 amperes during steady state. So we should consider this only. So 0.4 into 40 is how much? 0.4 into 40. Okay, so there is a calculation mistake, I guess, over here, because 0.4 into 40 is actually 16. So 230 minus 16 will be, so 230 minus 16 is 200 and how much? 214 volts, right? So this will be somewhere around, yeah. So this will be 214 root 2. Okay. So yeah, 0.4 into 40 is 16. I considered that as 1.6. So yeah, 214 into root 2 is 302.64 volts. Okay, and minimum will be how much? 30 minus 214. 214. So 302.96 minus 10. So 292.64 volts. Therefore, your V naught is going to be somewhere around 297.64 volts. Correct. Yeah. Okay. So the output voltage is actually 297.64 volts. Okay. Because your V input is 230. Right. So yeah. So which are the correct statements from the following options? A low power factor leads to higher line losses as compared to a high power factor for the same load ratings. In a rectifier capacitor filter, a higher power factor leads to higher current drawn from the input source. For the same load ratings, unity power factor can be achieved with a non-zero value combination of resistor, inductor, and capacitor. Higher diode conduction time in the rectifier capacitor filter lowers yield voltage ripple across the output. So, which of the following are true? Low power factor leads to higher line losses as compared to high power factor. True. So, if you have lower power factor, it means the reactive power Q is higher, therefore your current will be higher. In a rectifier capacitor filter, a higher power factor leads to higher current drawn. No. Higher power factor means lesser current drawn. So lesser current will be drawn. Unity power factor can be achieved with a non-zero value combination of R, L, and C. True. You can do resonance and get unity power factor. Higher diode conduction time in rectifier capacitor filter lowers the voltage ripple across the output. So what would lower the voltage ripple across the output? So you know that from the you have something like this. So if your diode conducts for longer, right? If your diode conducts for longer, obviously the ripple will be larger, correct? So this is something like this. If your diode conducts for longer, then what you will see is something like in steady state. But if your diode conducts for shorter period, you will see something like, okay. So this is of course wrong. So higher diode conduction means more will be the capacitor voltage ripple. Okay. Okay. So some simple problem for a 230 volt 50 hertz power supply. Calculate the power factor for the following figure. So it's a 50 hertz power supply. So what will be the power factor? Power factor will simply be what is the phase shift of In with respect to Vin. Correct? So always find out from the end. Correct? So your omega L will be equal to 2 pi into 50 into 6.37 millihenry. Correct? So that is going to be 6.37 into 2 into 3.14 into 50. So that will be somewhere around 2 ohms omega L, and your 1 by omega C will be 1 by 2 pi into 50 into 1.59 milli. Okay. So that will be 2 or 100 into 3.14 into 1.59. Okay. 9.26 into which will again be equal to 2 ohms. So you see that your omega L equal to 1 by omega C. Correct? So you see that this impedance and this impedance are kind of cancelling out, right? Because your total impedance in this branch will be equal to what? Is that equal to omega L minus 1 by omega C, correct? Or if you have to write it in J terms, it will be something like omega L. So J omega L minus J by omega C, correct? So J into omega L minus 1 by omega C. Okay. So what you will get is J into 2 minus 2, which is equal to 0. Okay. So the impedance is 0. Therefore, impedance is 0. So if you tell that the impedance is 0, Correct? If you tell that the impedance is 0, what you actually get is a direct short across the 40 ohm resistor. Correct? You get a direct short across the 40 ohm resistor. Therefore, your Z in, the input impedance that you see, Z in, will be equal to simply 20 ohms and then a short, right? So just 20 ohms. So it's a purely resistive input. Therefore, the power factor will be unity power factor, correct? Because it's just a resistive input. Okay, because you see that omega L and 1 by omega C are kind of cancelling out. Okay, so it will be a direct short across a 40 ohm resistor. Therefore, your input impedance is just 20 ohms, and yeah, the power factor is unity. Okay. Okay. So, what does zero power factor indicate? Zero power factor occurs when the load is purely resistive, purely capacitive, purely inductive, partially capacitive. So, zero power factor ZPF occurs when the load is purely capacitive or purely inductive. Okay, that is, let's say your voltage is Vm sine omega t, then your current will be exactly Vm by Z, Vm by mod Z sine omega t plus 90 if it's capacitive and minus 90 if it is inductive. So plus for leading current and minus for lagging current. Okay. So leading means it's capacitive and lagging means it is inductive. So zero power factor means, so obviously you know that the power factor which is cos phi is cos 90. So therefore power factor is 0. Okay. So zero power factor occurs if the load is purely inductive or purely capacitive, and of course your current will be something, if your voltage is like this, your current will be something like this. Either it will be lagging by 90 degrees in case of inductive load, or in case of capacitive load it will be leading by 90 degrees. Your current will be like this and your voltage will be like this. Okay, pretty simple problem. And finally we go to this problem. Next, the voltage applied to a load is V is equal to 230 cos omega t plus 20. Current drawn by the load is 5 cos omega t. So your voltage is leading by 20 degrees, correct? And current is just 5 cos omega t. Therefore, with respect to current, therefore the power factor is what? Power factor is simply cos 20. And what about whether it is leading or lagging? Current is lagging, so your power factor is cos 20 lagging. Correct? That is the phase difference between both. So it is cos 20 lagging. Okay, cos phi is lagging. Okay, so we just saw one set of problems. The solutions for the other set of problems is there in the portal as well. So, but till this point, if you guys have any doubt, this is the right time to ask. I'll just have water. Just give me a 2-minute excuse. Yeah. Okay. So if you guys don't have any more doubts, we'll just go ahead and see the rest of the problems. But however, the solutions for all of these problems are already uploaded in the portal. Okay. Am I audible first? Let me check. Okay. Yeah. So consider a capacitor filter full bridge rectifier which uses a resistor based inrush current limiting. The resistor has a nominal value of Rs with a tolerance of plus minus 10%. If the supply voltage is 230 volt plus minus 20% RMS, calculate the minimum value of Rs if the diodes used are 1N4007. Okay, so 1N4007 is so 1N4007 is a commercial diode. Okay, so calculate the minimum value of Rs. Is the question? Just a second. Okay. So this is similar to what we have seen earlier as well. So Rs can vary plus minus 10%. Okay. Supply voltage V in is 230 plus
Your
minus.
screen is not visible.
Oh, okay. Just a second. Yeah. Yeah, so in the ratio question, why voltage ratios are taken? Because the question asked was R1 by R2. Since these are only resistors, I can always take VR1 by VR2, right? VR1 by VR2 will be equal to R1 by R2. Okay. So, and they have also given that neglect the voltage drop across the MOSFET. Okay. So, yes, you can do that. If your I is same, correct, then R1 by R2 will be equal to VR1 by VR2. Okay. Okay, so the time is 7:30, so we'll just go through the solutions one by one. Okay, so of course you know that you designed the resistor for the worst case condition, correct? That is under the worst case, meaning your voltage will be 230 plus 10%. So that is your V max, correct? V max will be 230 plus 0.2 into 230. Okay, which is 276 volt. So that your Vs max is going to be 390 volts, correct? So your maximum current, when can it occur? Maximum current I max is equal to V supply max divided by R minimum. Okay, so we need to design considering this scenario. So you know that your Rs could vary between plus or minus 10%. So Rs minimum is 0.9 times Rs, correct? So this is your Rs minimum because it is Vs max by R min. So you need to take the minimum R min. And of course, you need to consider what is Vs maximum. Okay. And you go to the data sheet, you see that it is given that it can withstand a non-repetitive peak surge current. Peak surge current is 30 ampere according to data sheet. Okay. According to data sheet, it can withstand 30 amperes. Therefore, considering I as 30, you design it so that your I remains less than 30 or your Vs max by R min should be less than 30. Okay. So based on that, your Rs should be more than this particular value, that is 14.45 ohms, so that your current is less than 30 amperes. So this is very similar to what we have done. We have seen 2-3 problems already. So yeah, just go to the data sheet, you will get what is the non-repetitive peak surge current rating. Okay. So based on that only, this is calculated. Okay. And calculate what is Vs max and Rmin and just plug it in over here, you get the answer. Okay. Okay. So continuing with the question number 1, calculate the loss associated with the resistor in question 1 if the peak value of input current is 10 ampere and the conduction angle is 22.6 degrees. Okay, assume the current to be a square waveform during the conduction period and use nominal value of resistance. So they are asking us to find out the loss in the resistor 1. So what is the loss across a resistor? We just discussed about it. IRMS square R. R is given. We just need to find out what is IRMS. They have given that current is a square waveform during the conduction period. The conduction is for 22.6 degrees. So during that conduction period, the current is a square waveform. I just need to find out the RMS value of a square waveform, right? And then find out the losses. Simple, right? So the current is given as 10 ampere. So you know that during the conduction period, that is during this 22.6 degrees, the current will be 10, right? So during the positive cycle, it will be positive. During the negative cycle, it's going to be negative. So plus 10, minus 10, plus 10, minus 10. And it happens only for alpha period. Okay. So what is the RMS value of this particular waveform? RMS, you can of course find out by the definition that it is going to be 1 by 2 pi integral for a period of alpha, integral alpha, correct? So it is repetitive, therefore I can write 2 into, okay, integral alpha, and then it is a square waveform, therefore 10 d omega t. Okay, so 10 square d omega t. Root means square, right? I can write something like this, or thumb rule for a square waveform, RMS value is equal to your amplitude, which is 10 amperes, into root over T on by total capital T. Okay. So here the T on is alpha for period of pi. For every pi interval, the conduction angle is alpha. Therefore 10 into root over alpha by pi. Okay. So this is how you find out the RMS, or you can write 10 into root over alpha in degrees divided by 180. Okay. So this is how they have written that the I in RMS is Im into root over alpha by pi. So this is basically 10 into root over 22.6 by 180. So this turns out to be 3.54 amperes. Alpha is 22.6. Okay, 3.54 amperes. This is your I in RMS. Therefore, your loss will be I square R, right? So I in RMS square is 3.54 square into R is given as we calculated it as 14.45 ohms, correct? R is 14.45 ohms from the previous question. Therefore, the loss will be I in square into R, okay, which is 181 watts. Okay, simple question, right? In the question itself, they have given that assume the current to be a square waveform. So you know that if your Vin is something like this, during the conduction period alone, your current will be how much? During the conduction angle in steady state only, of course, it will be something like this is your input current. Okay. So the output current will obviously be the rectified version of this. Okay. Okay. So it's again a simple problem, I would tell. If you have any doubts, please do stop me or you can write in the chat box. Okay. So continuing with the question 1, if the forward voltage of the diodes is 0.5 volts. So you have 4 diodes, as you know, right? You have a resistor and then You have 4 diodes. Forward voltage drop of each of the diodes is 0.5 volts. So this is 0.5 volts. RS was 14.45 ohms. Okay. 0.5 volts, and the output voltage ripple, that is delta V, is 25 volts. Calculate the efficiency. Okay, use nominal values of all parameters, ignore tolerance. So tolerance is ignored. So plus or minus 10% is of course ignored. Okay, therefore your V in or V grid, I would call it. Okay, V grid is 230 volts. So 230 volts is your V grid, and you know that your IN RMS is 3.54 amperes. We just calculated it in the previous question. IN RMS is 3.54, right? 3.54, correct? So V in would be what? V in will be V grid minus IN RMS into R series, correct? What we define as V in is this. So this is your V in. Okay.
Sir, what is V grid?
V grid is this. V grid is 230. This is what they have given right in the question. Supply voltage is 230 plus or minus 20%. So this is your V grid. Okay. Of course, we are not considering the tolerances because they have asked us to ignore the tolerance. Okay. So V grid is 230 volts minus IN RMS is 3.54 into 14.45. So this will be your V in RMS. So V max will be what? V max will be V in RMS into root 2, and V min will be V max minus delta V. Delta V is 25 volts. Okay, this will be your V min. So what will be V naught? V naught will be the average of, sorry, V max plus V min by 2. Okay, simple, right? We just calculate what is V in, and from there everything follows. So yeah, this is what we have done. That is see, correct. So the input I naught, you know what is I naught? Yeah. So one thing is, before we proceed further, okay. So one thing was your V in is something like this, correct? So your V in is a voltage that you see over here. Okay, and you know what is Vmax and what is Vmin from this, right? So V naught is Vmax plus Vmin by 2. Okay, so let me take a new slide. Actually, there's a small clarification in the solutions that they have given, so that's why I'm solving this. Okay. So point is V naught is, I don't know why, V naught is Vmax plus Vmin over 2. Okay. So you know efficiency is what? V naught I naught divided by V in I in. Okay. So this is going to be, what is V naught I naught? V naught you will calculate from here, but what about I naught, right? So remember that this I naught is actually I naught average. Okay, because you obviously do not have any resistor over here wherein you can find out I naught RMS square into R. It is just a static I naught that you are going to get. Okay, so your I naught is actually I naught average. So what will be I naught average? How do I calculate I naught average is the question, right? So the trick is that, okay, so in the input side, we just saw sometime earlier that the input current is something like this, correct? So this is your input current. If this is your input current, The output current will be something like the rectified version of this, right? So what will be the output current? Output current will be something like rectified version. Okay. So this will be your output current I naught. So what is the average value? I naught. So what is the average? Average is the normal 10 amperes into T on by T. Correct? That is the area by time. So what is area? 10 into, this is for alpha. So yeah, so 10 into alpha over pi. Okay, so this will be your I naught. Did you get it? So this will be your I naught average. Okay, so we just go over here. That's why they have written I naught as Im into alpha over pi. Okay, input current is something like this. Therefore, the output current will be the rectified version. Correct?
So could you please label that?
Yeah, sure. See, you see over here, right? So what happens? You forget about this rectification. You forget about the current and all. So whatever is the sinusoidal input over here, it gets rectified over here and comes something like this. Correct? You forget about the capacitor. What happens is, whatever sinusoidal voltage you have over here, it gets rectified at the output, right? Because of the diodes, because of the alternate switching of the diodes. Now you imagine what would happen to the current, right? The current was something like this. So what will happen at the output? It would get rectified, right? That is why I'm telling that, see, your input current is uh, something like this. Okay, something like this. So what will be the output current? Output current will be the rectified version, wherein this is your pi, this is your 2 pi, and so on, and this period is your alpha. So what is the average value of this waveform? Average value is simply the area by time, right? So that is 10 into alpha over pi, correct? So 10 into alpha will be the area over the time period is pi. So 10 into alpha by pi. That is why I naught average is Im into alpha by pi. Okay. Is this understood how we are getting I naught? Okay. So
Yes,
now
sir.
that we get I naught, we go back to the original thing. Yeah. So this is how we got I naught. So now if you have I naught, we can calculate what is V naught I naught by V in. Okay, you know what is I in RMS, you know what is V in RMS. Okay, 230 minus 3.54 into 14.45. This will be your V in. Okay, so you calculate what is V in, you know what is I in. Okay, so let me write over here. So 3.54 into 14.45, right? So 230 minus 51 is 179. So it will be 179 into so this is actually your input. So you should take the VN as over here it should be the grid voltage, correct? Because the total efficiency is what you want to calculate from here. Okay, so it will be 230 volts into 3.54, correct? And V naught A naught will be the average of this. I will not calculate right now, but just it's V naught into I naught is found out to be 1.24 amps. 1.24. Okay. So this will be the efficiency. Okay, got it. So this is your RMS, V grid RMS, IN RMS. Okay, and this is your V naught average and I naught average. Okay. Simple, right? So V naught you can calculate from here. Okay. Yeah. Okay. So till this point, is it fine? Is it understood how we did so far? If this is understood, now you can understand that in this particular efficiency expression, we have only considered the voltage drop across this resistor. But they have also told that there is voltage drop across the diodes. There are 4 diodes in total. So there would be a drop of 4 into 0.5. That would be the voltage drop. Correct? So what you will see is that the voltage actual Vn will be V grid minus In into Rs minus 4 into, or since there are only 2 diodes conducting at a time, 2 into Vd. Correct? Minus 2 into Vd. Understood, right? One is the drop through the resistor and one will be the drop due to the diode. So that also needs to be considered. Even though that is very small, it would be kind of a little bit insignificant. You should consider that. And then only you will find out what is your V naught. Okay. So it turns out to be the efficiency. Yeah. So from this only you can calculate what is the efficiency. You should consider the diode losses as well. Okay. Yeah. So we'll move on to the next question. Increasing the value of filter capacitor in the full bridge rectifier leads to what? Increase in output voltage ripple? No. Decrease in output voltage ripple? Increase in peak input current? Correct. Decrease in output voltage ripple? No change in peak input current? No. No change in output voltage ripple? Increase in peak input current? No. So calculate the value of the inductor in the circuit below such that the power factor is unity. So you want to keep the power factor unity. If you want to keep the power factor unity, Zin should be resistive. Correct? So if Zin needs to be resistive, your L and C should kind of cancel out. Okay, that is they should be in resonance. Therefore, omega L should be equal to 1 by omega C. Okay, or L is equal to 1 by omega square C. Okay, so everything is given. You just need to calculate 1 by 2 pi into 50 the whole square into C is 1 millifarad. You can calculate what turns out, what is going to come over here. Correct? It should be in resonance. Yeah. So it turns out to be 10.13 millihenries. Okay. A load voltage is of the form V naught equal to 325 cos omega t minus 30. Load current is I naught 10 cos omega t. Calculate the power factor. So you see that your load voltage is lagging. Voltage lags current or current leads. Therefore, it's a capacitive load. Capacitive load, RC load. Okay, capacitive RC load. And what is the power factor? Power factor will be cos 30 leading. Current is leading, right? Or voltage is lagging. So cos 30 leading or root 3 by 2 lead. Okay. Yeah. So calculate the active power drawn by the load in question 6. So again a simple problem. Active power is P is equal to Vrms Irms cos phi, correct? Or Vm Im by 2 cos phi. So just compute, substituting the given parameters. That is Vm Im by 2 cos phi. So 325 into 10 by 2 into cos 30. Okay. So determine the type of load. Because it's a leading load, you know it's an RC load, correct? Yeah. Okay. A relay coil is used to limit the inrush current in a full bridge rectifier and is controlled using the circuit shown in figure. Calculate the value of resistance if the relay coil must be activated at t equal to 1 second. So at t equal to 1 second, I want the relay coil to act, which means that V plus needs to be 8 volt at t equal to 1. Okay. So the RC charging circuit needs to be such that the capacitor voltage increases to 8 volt from 0. You know that the capacitor voltage will charge from 0, right? So I want so it will charge from 0 and it will hit whatever is the supply voltage, correct? Supply voltage is 15 volt. So whatever is the supply voltage is 15 volt, it will hit 15 volt after a long time. But what we want is, we want the voltage to go to 8 volt at 1 second. 8 volt at t equal to 1 second. So you know that the capacitor charging is Vc is 15 into 1 minus e power minus t by Rc, correct? So Vc should go to 8 volt at t equal to 1. 1 minus t is 1 divided by R into C. C is 10 micro. From this expression, you can find out what is R, correct? So yeah, it forms an RC circuit. So Vc is 15 into 1 minus e power minus t by tau. And you want the relay coil to operate at 1 second. Therefore, this voltage should be 8 volt at 1 second. Okay. Therefore, you just substitute and you get what is R. Okay. So in order to remove the exponential, you need to take a natural logarithm, ln, and you get what is R. Okay. So the last question for the day, and we are also done with time here. So which of the inrush current limiting techniques is the best? Resistor, NTC, thermistor based, transformer based, relay based. So from the lecture slides only, we would have studied that all these methods are kind of lossy. What we generally prefer is the relay based method. That is, you have a resistor in series and then you bypass it using a switch later on. Correct? This is the best method. Okay. So this is kind of a non-lossy method during steady state. Okay. Okay. So this is what we wanted to discuss today. We have seen a total of 19 problems, and the first 10 problems that are given over here are already solved in the portal itself. If you go to your portal in PTEL, you can actually see this particular file. So that's why I have not solved each of them individually, but the remaining 9 problems are kind of new to you guys. So I have solved them. Okay. Yeah, and don't forget any losses that are given in the problem. Okay. That is the resistor loss due to the series resistor or the diode drop. All of those losses need to be considered. Okay. So this equation 0.636 into Vm minus 2 Vk. So where did we see this question? 0.636. Can you tell the question number? Which question? Point 636 into Vm minus V2 Vk. Okay, so I am not aware where this question came, so you can just tell. Or else others, if you have any doubts, you can let me know now, or we can close for the day today. General equation for full wave. Okay, so one thing is I would ask you guys not to memorize any equations. Okay, just try to derive it, or not derive it. You just use the first principles. Okay. So I'm not aware of this particular equation, 0.636 into Vm minus 2Vk equal to Vtc. Yeah, but if it works out, yeah, very well, you can use this. Okay, so yeah, thanks. So, okay, so if you guys don't have any other doubts, we can close for the day. Thanks for attending. So have a great week ahead, and yeah, good night, everyone. Go through the questions. Of course, the slides will be uploaded in the drive. I hope you have access to those. Thanks, Akshit. So I hope you have access to those slides as well. Go through the questions, try to solve as many problems as possible, and yeah. Okay. Okay, then. So then I will close the session. Thanks for attending. Have a great week ahead, and good night.